Ever wondered what makes ECL so fast? Welcome to the world of emitter-coupled logic, or ECL for short, a digital logic family that's synonymous with speed. At its heart, ECL employs bipolar junction transistors to craft logic gates, the building blocks of digital circuits. But what sets ECL apart is its high-speed operation. When the need for speed is paramount, whether it's in high-frequency communication systems or high-speed computing, ECL comes into play. Now imagine a pair of transistors, NPN or PNP, that are coupled at their emitters to form a differential pair. This is the basic operation of ECL. The magic of differential signaling, the low output voltage swing, and a focus on the current mode of logic are just a few key aspects that make ECL a standout in the realm of digital logic circuits. So if speed is what you seek, ECL might just be your answer. Let's dive into the heart of ECL, the differential pair. The differential pair is the cornerstone of ECL. Picture two transistors, either NPN or PNP, their emitters coupled together to form this pair. The collector of one transistor is hooked up to the power supply while the other's collector is grounded. Now the magic of ECL lies in differential signaling. What does that mean? It's all about the voltage difference between the two emitters. This difference is what conveys the signal, and it's what gives us our differential output. But how does this process exactly work? Well, when an input signal is applied to the base of one transistor, it changes the current flowing through that transistor. This in turn alters the voltage at the emitter of the other transistor. The result is a voltage difference between the two emitters that corresponds to the input signal. Let's picture a seesaw in a playground. When one side goes up, the other side goes down, creating a balance in the system. That's similar to how ECL operates. When the input signal rises, the voltage at one emitter decreases, while at the other emitter it increases. This balance forms the essence of differential signaling in ECL. But what happens when both input signals are equal, or when there is no input signal at all? In such cases, the voltage difference between the two emitters is nearly zero, and there is no change in the output. This is the zero differential state, and it's a critical aspect of ECL operation. So what we've learned is that ECL, through the use of differential pairs, manages to deliver high-speed operation. It's like a finely tuned orchestra, where each transistor plays its part in harmony with the others, creating a symphony of differential signaling. And that's the basic operation of ECL for you. It's a fascinating journey into the world of high-speed digital logic, where differential pairs take center stage and play the lead role. With this foundation, we can now explore the unique characteristics of ECL. ECL is not just fast, it brings a lot more to the table. When it comes to speed, emitter-coupled logic, or ECL, is the veritable hair of the digital logic family. But speed isn't its only forte. Let's delve into some of the key characteristics that make ECL stand out. First up is its high-speed operation. This is where ECL truly shines. The incredibly fast switching speeds make it a top choice for applications where every nanosecond counts. Imagine a bustling city where everyone's in a rush. That's ECL for you, always on the move, always fast. Next, we have the low output voltage swing. ECL operates with a small voltage swing, typically around 0.8 of a volt. This minimal swing helps to reduce signal degradation and improve noise margins. Think of it like a well-rehearsed ballet performance. Every move is precise and controlled, ensuring a flawless performance. Then there's the noise immunity, thanks to the use of differential signaling. This means ECL is less susceptible to common mode noise, making it a bit like a Zen master, unperturbed by the surrounding chaos. Finally, ECL is often referred to as a current mode logic. Why? Because the logic levels in ECL are determined by the current flowing through the differential pair, not the voltage. It's like a river, where the current dictates the flow, not the depth of the water. But like everything in life, ECL isn't perfect. It has its challenges, like higher power consumption and heat generation compared to other logic families. However, advancements like Advanced Emitter-Coupled Logic, or AECL, have been developed to address some of these concerns. So, what does all this mean? It means that while ECL might not be the right fit for every application, in scenarios where speed, precision, and noise immunity are paramount, it's a formidable contender. These characteristics make ECL a robust choice for certain applications. Now, let's see how ECL shapes the world of logic gates. In the realm of ECL, the implementation of logic gates like NAND, NOR, and OR is somewhat distinctive. Typically, an ECL logic gate employs a differential pair along with additional circuitry to execute its function. For instance, to construct a NAND or NOR gate, the differential pair is configured in such a way that it delivers the desired output based on the given inputs. Similarly, for AND or OR gates, the differential inputs and outputs are manipulated to achieve the necessary logic operation. It's intriguing to note that while the fundamental operation remains the same, the configuration of these differential pairs and additional circuitry varies, giving each ECL gate its unique characteristics. This is just one of the reasons why ECL is such a fascinating and important part of digital technology. ECL's implementation of logic gates is quite unique, isn't it? Understanding ECL requires getting familiar with some specific terms. Let's delve into this exciting world of ECL terminology and learn about the power supply requirements of ECL. First up is the emitter-coupled pair, or ECP. This is the basic differential pair configuration used in ECL circuits. It consists of two transistors, either NPN or PNP, coupled at their emitters. The collector of one transistor is connected to the power supply, while the other's collector is connected to ground. The voltage difference between the two emitters provides the differential output. Next, we have the current source. In ECL circuits, a constant current source is used to bias the transistors in the differential pairs. This biasing is crucial for the differential pair to function correctly, as it sets the operating point of the transistors. Active termination is another important term. ECL circuits typically use active termination techniques to minimize signal reflections and maintain signal integrity. These techniques include the use of resistors or other components to absorb signal energy and prevent it from reflecting back into the circuit. Now let's talk about power supply requirements. ECL requires two types of power supply, a positive one, denoted as VCC, and a negative one, denoted as VE. The positive power supply is connected to the collector of one transistor in the emitter-coupled pair. The negative power supply, on the other hand, is used for biasing and is connected to the emitter junction. Understanding these terms and the power supply requirements of ECL is essential for anyone working with ECL circuits. Remember, ECL is all about speed, and these terms help describe how that speed is achieved. With these terms in our arsenal, we can now explore ECL's applications and challenges. ECL, like any technology, has its pros and cons. On the upside, ECL's high-speed operation makes it a standout. Its impressive speed has led to its application in high-speed mainframes and supercomputers where every microsecond counts. Beyond computing, ECL's prowess also extends to high-frequency communication systems, making it a valuable asset in high-speed data transmission applications. However, ECL is not without its challenges. Its high-speed performance comes at the cost of increased power consumption. This in turn leads to substantial heat generation, necessitating efficient heat dissipation mechanisms. Managing these heat levels can be quite a task, especially in compact systems where space is at a premium. Despite these challenges, advancements in ECL continue to make it a viable option. Advanced versions of ECL, such as the advanced emitter-coupled logic, have been developed to address the power consumption issues, thus keeping ECL in the running in the world of digital logic. So how does ECL stack up against other logic families? When we compare ECL with complementary metal oxide semiconductor or CMOS, we find that ECL is substantially faster. This speed advantage makes ECL a preferred choice for applications where swift digital logic is crucial. However, ECL consumes more power than CMOS. This higher power consumption can be a drawback, especially in energy-conscious environments. Consequently, CMOS has gained popularity due to its lower power usage and scalability. On the other hand, if we compare ECL with transistor-transistor logic, or TTL again, ECL comes out on top in terms of speed. But like with CMOS, ECL has a higher power consumption than TTL. This trade-off between speed and power consumption is a key factor when choosing between these logic families. While ECL may not be the perfect fit for all applications, its speed makes it a strong contender in the world of digital logic.